Okay, we are beginning a new unit. Let's just backtrack here so you can get a view of that. We're in Unit 3. There we go. And Unit 3 is all about energy conversion, changing energy from one form to another. And it's also about renewables, renewable energies. 3.1 is types of energy. And that kind of looks like it's going to cover things in broad strokes. And then maybe it probably is going to get into some specifics. And then we'll kind of get into some other specific topics with the other chapters there. So let's click on 3.1. Let's go to explore. And let's begin. Go ahead and draw your Cornell Note templates. Make sure you put your date. Using their question for Explore 1. What are two main types of energy? What are two main types of energy? And what are some examples of these types of energy? Question mark. Okay. Question mark. All right. So, what are two main types of energy, and what are some examples of these types of energies? All right. So, let's go ahead and have you write down what you know. Go ahead and hit pause. Okay. What I know or think. Okay, well, hopefully you wrote down a few things that come to mind. And now we're going to take and put this stuff, all this text, into some meaningful notes. Roman numeral 1, kinetic energy. Kinetic energy. Sometimes we abbreviate that as KE. Sometimes we call this energy of motion. There it is. Energy, kinetic energy is the energy of motion. We'll write that down. Known as energy of motion. Okay, sorry, I was kind of doing some handwriting there. Known as energy of motion. It is proportional, see that in red there, proportional to the mass and the square of its velocity. It's proportional to its mass. So kinetic energy is equal to something like mass, and it says it's also proportional to the square of its velocity and the square of its velocity. And they give us a little equation over here. And there you go. Let's go and write that in red here. We got kinetic energy is equal to half times, there it is, mass, directly proportional to mass, and directly proportional to the square of its velocity. Okay, so you probably want to make sure to know that equation, okay? They've got a little video there. So they go and talk about different examples: fish swimming, boat sailing, people running, carousel spinning, all these things, anything that moves. These are examples of kinetic energy. But take a look at the next paragraph. However, there is kinetic energy in many objects that is not as easily noticeable. Okay. Plucking a guitar string, that vibration, that quick vibration of the string, producing sound. This form of kinetic energy is sound energy. So maybe we can say letter B. Some examples of kinetic energy are obvious. ... Others not so much. I.e., sound energy. Maybe you wouldn't think of that necessarily as a form of kinetic energy. And of course, I want you to read these paragraphs. My goal is not to take up all of our time reading all this text together. I'm trying to show you the greatest hits, right? Take a look at the next paragraph. This form of kinetic energy, what are they talking about here? You rub your hands together, you feel the warmth. The rubbing motion causes atoms at the surface of your skin to move faster, increasing their kinetic energy. This form of kinetic energy is called thermal energy. So we're talking about forms of kinetic energy that are not so obvious. Thermal energy. Okay. You may want to watch that video there. Now we move into another type of energy, potential energy. We often, you may have learned this as the energy of position, Roman numeral 2, elastic potential energy. What can we say here? Potential energy is the energy of an object due to its location, shape, or position. There are many forms of potential energy. Perhaps the easiest to understand intuitively is elastic potential energy. So maybe actually elastic potential energy, among others. There's many forms of potential energy, okay? So first off, let's just define potential energy. Potential energy is also known as the energy of position. Okay. If I put a something on the countertop and I push it off the countertop, maybe it's a glass. Depending on how high my counter is, that's going to affect the potential energy in that glass. If I take the glass and put it on top of the roof, much higher, that too is going to affect, it's going to cause my glass to have a greater potential energy. Okay, so well, let's see here. We talked about energy position. Let's go ahead and click on this one here. Okay, but if you read the following sentence, it says, when a rubber band is stretched, it has elastic potential energy. Think of the rubber band as having the potential to snap into motion if it were suddenly released. Okay. If I click on this definition here, We're trying to understand this. The capacity to do work stored in a material. Okay, a rubber band, pull it from its neutral position, pull it, and all of a sudden you know that that rubber band has the capacity to do something, right? All because of the change of its shape. Okay, the capacity to do work. So maybe we want to write that down, okay? Elastic potential energy. Okay, that's what PE stands for, potential energy. The capacity to do work stored in a material. Stored in a material or physical system that can change shape. Can you think of some other forms of elastic potential energy? Okay. If you take a look here at this here, elastic potential energy has numerous everyday applications, such as the use of suspension springs in cars. So yeah, a spring. I imagine in your pens, you have little springs that allow you to click your pen. So you're using elastic potential energy every time you use a pen like that, right? I'm going to close this up there. Okay, so kind of jumping down here, we can see that elastic potential energy, um, they give one of a spring. So i.e. a spring is a good example. Remember, a spring looks something like that, right? A spring, right? We would say that the potential energy elastic, because there's different forms of potential energy. So we're defining this as potential energy that's elastic is equal to 1/2 times K times X squared. Okay, now hopefully they're going to define this for us, right? Where K is the spring constant, which depends on the particular properties of the spring. Well, that makes sense. Um, you could have a spring that's made out of iron. You could have a spring that's made out of copper. All these different metals are going to have different attributes, right? So this constant uh, value here depends on the material. This is your spring constant. Depends, or I should say it varies. This varies depending on material, other properties as well. Okay. And then X, X is the distance the spring is compressed or stretched. You can squish a spring, right? You could go ahead and you can elongate it. Right? Or you could squish it. Right? So we could say this has been compressed, squished, or you could say that it has been elongated, or you could say stretched out, right? And these distances, that's what they're referring to. The x value represents the distance the spring is stretched or compressed. Represents the distance spring is stretched or compressed. Okay. Well, there you go. So we've kind of parsed out elastic potential energy. Make sure you watch those videos. Now, there's other types of potential energy. There's gravitational potential energy. So let's go ahead and do this here. We're going to say that this was A. Let's go ahead and make this one letter B. I'm going to call this gravitational potential energy. Okay. Make sure you read the paragraph there, but this is this idea that, you're stuck on the earth because a gravitational pull is pulling you down. If we were to have you climb up to the top of the second story at the school, you would have a certain amount of potential energy stored in your body because you've increased your height, right? Well, what happens if you go to the tallest building in the world? You got even more potential energy because the height has changed, right? So in green, it says the more an object is lifted against the force of gravity, the more energy it will have once it is released. Gravitational potential energy is said to be stored in the object when the object is lifted. Okay. Energy that is stored in an object, the higher it is lifted. In an object, the higher it is lifted, the greater the potential energy, the gravitational potential energy, right? It says it is denoted by PE, although to avoid confusion, it is sometimes written as PE grav, right? Or PE, you could just write down grav for shorts, okay? And we're just pulling that directly from the text there, right? Okay. Let's come back over here. Now they do give us an equation here as well, okay? So we probably want to write this equation down, okay? Potential energy, gravitational potential energy, remember this is PE, is the mass of an object times the gravity due to acceleration of the object times the height of the object, okay? Mass gravity and height. Okay. Gravity due to acceleration, which is 9.8 meters per second squared, equals 9.8 meters per second squared. Okay, we talked about that before. Downward, okay? All right, so look, we've gotten some useful equations here. An equation for figuring out the kinetic energy of objects, a equation for solving potential energy in elastic systems, and a equation for figuring out gravitational potential energy. Now we're going to move into another type of potential energy. We're going to talk about chemical and electrical. Chemical and electrical potential energy. Think batteries, right? Chemical reactions, energy stored in the food you eat, right? There is energy stored in the chemical bonds. We've talked a little bit about these things. Chemical potential energy is stored in the bonds between atoms and molecules. So we just said that. Chemical stored in the bonds between atoms and molecules. These bonds can be thought of as attractive forces between different atoms and molecules due to their structural properties. Chemical reactions release the chemical potential energy stored in the bonds. Okay, stored in the bonds between, okay, attractive, right? The bonds are attractive. Chemical reactions release. Chemical reactions, they break the bonds, therefore releasing the potential energy. Release the potential energy. Okay. Usually in the forms of forms such as thermal and light energy. Okay. Now, electrical potential energy is a little different. It's stored in electric fields between charged particles. Okay. So let's just kind of use a different color here. And we'll just kind of say that stored in electric fields between charged particles. Okay, we can use the principle of chemical and electric potential energy to discuss the function of a battery. Okay, so let's go and put this over here. We'll go and put down number 1. Batteries are a good example that models these types of potential energy. Okay. Okay. So what I would probably suggest here is you take a little bit of time to read this. Okay. But you can have a battery. You can have like a battery, right? And you can have a positive and a negative terminal. And you can take electrons and you can charge your battery by forcing electrons against their gradient into the negative terminal, and you can build a charge. Build a charge. And then after you have a when 100% charged, you can go ahead and take your battery, positive, negative, and then you can go ahead and hook a wire to it, right? You could hook a wire and your electrons would flow out, right? They would flow out from the negative terminal to a positive, right? And so these are just kind of giving you some examples of, and in the battery, you have, in this case, you have chemicals inside there, which are storing the chemical potential energy in there. Okay. So anyway, read about this. Okay. But they do give an equation here. Okay. And so we probably want to write that down. Number 2. The electric potential energy between two charges. This looks familiar, huh? This looks like Coulomb's law. Charge 1 and charge 2 is given by Coulomb's law, where we say the potential energy, electric, is equal to it looks like we've got a constant, times the charge of object 1 times the charge of object 2. All of that is going to be divided by the distance, okay? And here we want to say that K is Coulomb's constant, which was equal to, well, they don't provide that for us right here, but we have this in our past notes. And R is the distance between those charges, okay? Okay. Oh, let's see here. Okay, moving on here. Energy stored in fields. Let's see here. What do we have? We've talked about gravitational, chemical, and electrical potential energy. Let's draw a line. And A, B, C, we'll call this D, okay? D. Energy stored in fields. Okay, so here we're kind of shifting gears just a little bit. All electromagnetic waves, including visible light waves, are made up of electric and magnetic fields. Okay, so we're talking about electromagnetism here. These fields lie in planes that are perpendicular to one another, and they oscillate in phase with each other Like a mechanical wave, think a water wave or sound wave, electromagnetic waves carry energy from one location to another. However, unlike mechanical waves, electromagnetic waves do not need a medium in order to travel. They can move through a vacuum, think outer space. Okay, so let's start with this. We'll go and say number one, electromagnetic waves. They have an electric component and a magnetic component, right? So we're going to draw this out something like this. And we could say that your field has got a I'll draw a couple wavelengths here, right? And then I could draw a I'm trying to draw this so you can kind of see that there's these things travel perpendicular to each other. So you could have this one be like a y-axis, right? Positive and negative. And I guess we could say that this could be a z-axis. Z-axis. And we could say that this was positive and this was negative. And we're just trying to show that these things travel perpendicular. Maybe we would say that this was the magnetic part. And maybe this was the electro part. And they travel perpendicular. That symbol means to each other. To each other. Okay, this symbol means perpendicular. Okay, they travel perpendicular to each other. Okay. Probably also a little side note here. These don't need a medium to travel through. Unlike a mechanical wave. Okay, and that's why these things can travel through outer space. Okay, so refresh yourself on electromagnetic radiation, okay, with this little short video. Because electric and magnetic fields both possess energy, the total energy in an electromagnetic wave is the sum of the energy in both of these fields. Okay, so to calculate the total energy, the total energy in an electromagnetic wave, you have to take the sum, that means to add, of each part. Okay. Okay. Now this is interesting. each part, the electric and the magnetic, are going to be supplying equal amounts of energy. The electromagnetic energy density, U, is the amount of total energy per unit volume. In free space, it can be stated in terms of either the amplitude of the electric field, which is a capital E, or you could, an equivalent sort of expression would be to express it in terms of the magnetic field. Okay, and so you can kind of see those equivalents there. So let's just write this down here. Another equation. U, which is the density, right, is equal to 1/2. And they're going to give you what that little squiggly E looks like. Okay, but we're going to write that out right now. E, O, capital E squared, which is equivalent to 1, 2, mu 0, capital B squared. Okay, time to just kind of define these. We said that U is going to be the density of the energy. So electromagnetic energy density okay, is equal to 1/2. I guess we should go ahead and just put this down here. What is this term here? It is equal to, let's make that nice and large, 8.85, 8.85 times 10 to negative 12 coulombs squared times newtons times meters squared. Okay, you're going to get some new words here: permittivity and permeability of free space. Okay, and they also define for you what that mu 0 is. I'm going to use a different colored pen for that. Okay, and this guy is equal to mu 0 is equal to 4 pi times 10 to the negative 7 newtons times second squared divided by coulombs squared. Okay. All right. And we can speak of these in terms of amplitude of the electric field. So let me just change colors here. This could be referred to as amplitude of electric field. Or we could speak of it as in terms of the amplitude of the magnetic field. So they give these equivalents, right? Amplitude of the magnetic. Okay, so these are equivalent statements here. Okay. Okay, I know what you're thinking. I hope I don't have to do any calculations, right? Energy and wave frequency of the photons is related through the equation shown below, where F, okay, so now they're talking about particle, in the particle model of light, electromagnetic radiation is made up of small packets, okay, called photons. In free space, these photons travel at the speed of light, and the energy and wave frequency of the photons is related through the equations shown below. Okay, so number 3. Boy, this is a really packed chapter. Explore. For photons, okay, the energy and wave frequency for photons, their energy and wave frequency. For photons, we can relate them as follows. And so we have here is we have the energy of a photon energy of a photon is equal to h and f. Okay. No, let me just make that just a little bit easier for you guys to say just equal to h and f. Okay. Now, what is h and what is f? H is going to be Max Planck's constant. Planck's constant, you've heard of this before, and they tell us what that is. It is 6.63 times 10 to the negative 34 meters squared times kilogram divided by second. Okay. And then the F is the frequency of light. And remember, light travels at different frequencies depending on the type of color of light it is. If we're talking visible light, or if we're talking invisible parts of the electromagnetic spectrum, X-rays, gamma rays, radio waves, you're going to have different frequencies, right? Frequency. All right. Oh my goodness. All right, so let's see here. Going to the next paragraph. As the wave frequency of a photon increases, the amount of energy it contains also increases. Well, this is interesting. The higher energy forms of radiation contain so much energy. I mean, why is X-ray so bad for you, and gamma rays? Because they can knock electrons out of the orbits. They got that much energy. Okay. Higher forms of energy can knock out electrons from their orbits, right? A little fun fact there. So watch this video, it's very useful. The electromagnetic beam consists of photons. Therefore, its total energy density is proportionate to the density of photons per unit area within the beam n. As the number of photons increase, the beam energy density also increases. That makes sense. However, the energy density is also proportionate to the square of the electric field strength. This means that the photon density must also be proportional to the square of the magnitude of the electric field. Okay, so let's go ahead and write this down. We'll say that this is A. And we're just going to first write this equation here, okay? We're going to say that N is proportional to E squared, okay? And let's go ahead. This means that the photon density must be proportional. So remember that the definition here, N, let's see, its total energy density is proportionate to the density of the photons per unit area. Okay, so that's what that means. that guy. Sorry. And the density of photons per unit area within a beam. Okay, the photon density also must be proportional to the square of the magnitude of the electric field. So this is the magnitude of, that's the strength, magnitude of the electric field. And we're going to say squared. Okay. All right. So that's going to take maybe a couple readings from you on that paragraph just to kind of let that soak in, okay? But I wouldn't get too hung up on it right now. They're just being thorough here. And this is just kind of a survey, right? Energy and particles. Okay, now we're getting to some stuff that looks like more familiar territory for us. What do we want to say here? This was D. ABC. This was elastic energy. Let's make this Roman numeral 3, okay? And we're going to just drop this down. Okay, 1, 2, 3. We're just about finished here. Energy in particles. Okay, so you have learned that particles, atoms and molecules have energy because they move and interact with each other. They can be transferred between individual particles and therefore between larger macroscopic systems. Heat is the energy that is transferred between systems. There are 3 ways energy can be transferred: conduction, convection, and radiation. Okay, energy in particles, atoms and molecules can interact, right? Therefore, transfer energy between them, okay? Heat is the way we describe that, okay? And we can say that there are 3 ways of transfer. And we had our conduction, where the particles just collide with each other and the energy transfers between them. You have convection, where particles actually move from one location to another. You have natural convection, like heating up water or heating up air. Things spread out as they become less dense and they rise, and heavier particles sink back down. So you actually have movement of particles going on. Okay. So we said conduction is basically collisions. Let's see if they give us actually good working definitions down here. Colliding, we want to use those words. Okay, so high energy particles high energy particles collide with other particles, with each other, with cooler particles, and they with slower moving particles. Therefore, what do? They transfer some of their kinetic energy. Okay. Convection, we said, on the other hand, is when you have the movement of particles from one locale or location to another based on density, right? And they talk about artificial versus natural convection. And then they talk about a final method, which is your radiation. The final method of thermal energy, radiation. Make sure I got enough power here. Looks like I'm gonna die on my power, better be careful. Sneaks up on you like that. Sorry about that. I'll try to get this all plugged in here. There we go. Almost lost that. Okay, hopefully I'm still recording. Let me get that part up there. And let's try to get, we were on 3.1. And I believe that we were down here. Get this back to, that looks pretty close. We're talking radiation. So let me just drag this back over here. Radiation. Okay. What do I want to say about that? It occurs because all particles oscillate. Due to oscillation, that probably is the best way to say that, of particles. Emitting electromagnetic radiation. Okay. And energy in this case is radiated or carried away from the source by electromagnetic waves. All right. And you could think about that as if you got a fire and you put your hands over the fire, you're feeling heat because of convection. But if you stand to the side, you can still feel the heat because of the radiation that's going on. Okay. So, well, that was a lot. Okay, so just to kind of recap again, what was this all about? Because you're going to have to summarize it. What were the two main types of energy? We talked about kinetic energy and potential energy. And what are some examples of these types of energy? And we talked about a whole host of examples just now. So, your turn. Somebody asks you, what did Mr. Meyer talk about in class? What would be your summary if you were to summarize it? Okay, so go ahead and just give me a little summary paragraph, and we'll talk to you soon. Take care.